Continuing this with this homework, let's look at the next problem, which is problem number 26. It says write two complete balanced equations for each of the following reactions, one using the condensed and one using the Lewis structure. All right, so let's look at this first one. The condensed structure, it says 2-butene reacts with chlorine. So 2-butene looks like this. Between the 2 and the 3 carbon is going to be a double bond, okay? And so it's going to look something like that. And then you're going to have, so you have 1, 2, 3, 4, so that's butene. 2-butene has a double bond here. And to that, you're going to add chlorine. And what happens in this reaction is pretty simple. The double bond breaks, and each of these takes on a chlorine. And so it looks like this in this structure. And I'm doing it this way. Now, some people will just write the Cl here and the Cl here. I'm doing it the way I'm doing it. It helps make it clear. So this is 2-butene. In my mind, it makes it more clear. And this would be butane now, because there are no double bonds. And it would be dichlorobutane. It would be 2,3-dichlorobutane. And so that's what happens. Now the Lewis structure for this would be right here is where all the action is. You have 4 dots between these two guys. You have the C dot dot and C dot dot out here. And so, and I'm not going to write the rest of this. We'll just write CH3 here and CH3, even though you can write that with the dots all around. But this is where the action is right here. And then the chlorine is going to look like this. And essentially, what you end up with is the C with just 2 dots in between the center ones. We'll put this CH3 over here and CH3 over here. And now you have a hydrogen up here, a hydrogen up here, and down here you have a chlorine with all the dots around this chlorine, and a chlorine here with all its dots. And that's what it would look like under a Lewis structure. The next one is benzene burns in air. Now benzene is a cyclic hydrocarbon that looks like this. And every other bond is a double bond. It has a very unique structure. And each carbon has 1 hydrogen. Now, a combustion reaction, you end up with water and carbon dioxide. So if it burns in air, this is what ends up happening. And so all of this breaks apart to form this. You have to balance this, of course. You have 1, 2, 3, 4, 5, 6 of these. And you have 6 of these, so you're going to have a 3 here. And unfortunately, that's an odd number of oxygens. You have 12 and 3 is 15. So you have 7.5 here, and you know we don't like that. So we'll say that there are 2 of these. We'll change this one to 15 now. And this would be a 6 now, and this will be a 12. So you have 24 and 6 is 30 oxygens divided by, so it's 30. So it's balanced. So that's what it looks like. And then the Lewis structure is going to look something like this. You're going to have 4 dots here, and then 2 dots on this side, then 4 dots here, and 2 dots here, and then 4 dots here, and then 2 dots here, like that. And then this other stuff all is the same. O is going to be like this with the rest of it out here. And let's see. See if that's, let's see, with oxygen you have 12 total valence electrons, and currently we're going to have to put a double bond here to make it work out. Okay, and so that's 4, 6, 8, 10, 12. So that's all so that does that. Then that goes to water. We know that water looks like this. And then carbon dioxide, we'll start out with looking this way. Let's see how many we have. 4 and 12 is 16. We started out, we used up 4 to bond those two together, so that's 12. And if we put 1, 2, 3, 4, 1, 2, 3, 4 like that, I think we're going to need a double bond in here somewhere. 4 and 4 is 8. That leaves us with 4. Yeah, we need a double bond here and a double bond here. And that works it out. So you have 8, 10, 12, 14, 16, right. So there's what it looks like with the Lewis structure. Obviously there'd be 2 of these, there would still be 15 of these, there would still be 6 waters and 12 carbon dioxides. Okay, so that's according to the Lewis structure. Now, let's take a look at this last problem. Number 29 says ethylene can be produced by pyrolysis of ethane. How many kilograms of ethylene is produced by the pyrolysis of 1 times 10 to the 3rd kilograms of ethane, assuming 100% yield? I got to tell you, I don't know what pyrolysis is, so I'm going to have to look up what that is. After some digging around, I found out that pyrolysis looks like this. You take the underlying substance, which in this case is ethane, C2H6, and under heat you produce C2H2, which is ethylene or ethine, plus 2H2, and that's the process of pyrolysis. So you have 1 mole of this produces 1 mole of this and 2 moles of that. So if you take 1 kilogram, 1,000 kilograms, 1 times 10 to the 3rd kilograms of ethylene, or ethane, how many kilograms of ethylene will you produce? Well, first of all, this is 24 plus 6 or 28, so you have 1.0 times 10 to the 3rd kilograms, and there are 1,000 grams in a kilogram, and there are 30 grams in a mole. This is 6 plus 24 is 30. And this will tell you how many moles of this you have. And you have 3.333 times 10 to the 4th moles of ethane. And for every mole of ethane, you have a mole of this, so you're going to have 3.333 times 10 to the 4th moles of ethylene. And that ethylene is 24 plus 2 is 26 grams per mole. And that's going to give you the answer in grams. And so we'll change it back to kilograms since that's what they asked for. And if we do that, we get 866.7 kilograms of ethylene.